Okay.
Okay. Again. Hello, everyone. Sorry for the delay. I'm happy to introduce Maria Teresa Rotolo from CISA that will talk about the growth of Sobolev norms for completely resonant quantum harmonic oscillator in R2.
Thank you very much for the introduction and for the invitation, and thank you all very much for being here today, despite the bus strike that now characterizes this series of seminars. So the goal of today's seminar is to present a work that we just completed with my PhD supervisors, who are Beatrice Langella and Alberto Maspero. And it's related to the problem of growth of Sobolev norms for an equation, a Schrödinger type equation of some harmonic oscillators. I will now be precise. I hope that online everything works. In case, just let us know. So, maybe. Okay. The plan of the talk is to start with a broad introduction to the problem of growth of Sobolev norms and to give an overview of previous results linked with our work. Then I will state our result and give an idea about the main ingredients in our proof. So, just to start, let me describe very broadly, very generally, our equation. So what we consider is a Schrödinger type equation, where on the right-hand side we have the operator H0, which is the operator of the quantum harmonic oscillator in dimension 2. So minus Laplacian plus x1 squared plus x2 squared. Just notation for the variable x with the two components in R2. Then we have a time-dependent perturbation. I will be precise about it in a moment, but for the moment it's just to say that it is a linear time-dependent Schrödinger equation with this form. So to be precise about the perturbation, I need to introduce the scale of spaces in which we will consider our solutions. So it is natural to look at them in the domains of the operator of the powers of the operator H0 over L2. So we denote by HS the domain again of H0 to the S over L2, and this will be for us our Sobolev spaces. And the norm, of course, is the one written there, which is the L2 norm of H0 to the S applied to U, gives the S norm of U. With these ideas in mind, I can now start being a bit more precise on V. Indeed, we ask V to be 2 pi periodic in time. Then we ask the self-adjointness of the operator V for every fixed time. And finally, we ask V to be a bounded operator in this scale of spaces. So for every fixed S, we ask V to be bounded as an operator from HS to HS. For who is familiar with these ideas, V is pseudodifferential of degree 0, but I will define pseudodifferential operators later on. So for the moment, this is just the important fact to have in mind. So what is the problem that we consider in general? So given our equation with the potential V identical equal to 0, we are very familiar with the solution, which is given by the propagator of H0 applied to the initial datum U0 of x. So this results in the solution at time t. And thus, it is straightforward to see that all the S norms are preserved for every time. So there is no information to gain looking at the Sobolev norms. In general, of course, the interesting case is when the potential is different from 0. And in general, we are able to say that just the L2 norm of the solution is conserved due to self-adjointness. So with our notation, the L2 norm corresponds with the 0 norm. With the 0 norm in this scale, yes. So this is the only conserved quantity that in general we can look at. So the question that we ask is the following. Are we able to find some potentials V such that we have solutions of the corresponding equation which exhibit unbounded growth in time of some positive Sobolev norms? So this is the general question related to our problem. Following the literature in the field, if we find such potential V, we call it a transporter. This is just usual terminology for this kind of problems. Now, the idea is I'd like to motivate why we really ask for this behavior and we don't look at other norms or other requirements. So to this aim, let me just change a little bit for just for this slide, the setting. We know that the spectrum of the operator H0 is this discrete spectrum, which is given by the natural numbers shifted by 1 due to the dimension. And we can just write our solutions with respect to the basis En, which is an orthonormal basis made of eigenvectors. What happens? Does lambda n are the eigenvalues. What happens is that the solution at time t can be written with respect to this basis, and thus when we compute the S norm squared, this is equal to the sum of the eigenvalues at the power 2s times the modulus squared of the corresponding coefficient. So what we look at is a growth of the positive norms, since this indicates a transfer of energy in this frequency space towards the higher modes. So we are interested in this behavior since this is a sign of instability of our solution. And in the literature, again, these phenomena are known as weak turbulence phenomenon or energy cascade from low to high modes for this reason. So this is an idea of why we look for this kind of growth. Now, the other point which I think is important to motivate our problem is, of course, our previous results in the field. So this slide does not aim to be a list of previous results, but just an idea of what has been done strongly related to our problem to motivate our result. Because the fact is that the first works that have been done were works in which the authors found particular potentials which they proved to be transporters. In particular, we have in dimension 1 a work by Delors in 2014, and then in a subsequent work in 2019, Alberto has found a transporter which is universal, which means that all solutions grow in unboundedly in time. And then in R2, Thomann, so in our topological setting, Thomann found an example of a transporter. The turning point in 2022 is a paper, again by Alberto, in which he considers a class of Schrödinger equations, which of course contain our equation in particular. And he gives a set of sufficient conditions to verify on the operator V, on the potential V, to ensure that it is a transporter. So this is no more a particular example, but a construction of a general strategy that one can follow. Thus, the problem becomes that of understanding if this general strategy is somehow satisfactory, and thus to apply it. The first application is, again, in 2022. Sorry for the notation, these are two different works. 2022, a first application in which considering the problem in dimension 1, so in R, we are able to use this strategy and prove that instability is a very common phenomenon in dimension 1. So in particular, I will be precise later on about what genericity means in this context, but using this strategy, Alberto is able to prove that in dimension 1, almost any potential, let me say informally, is a transporter. Clearly, the main difficulties that one faces are the dimension in which we consider our equation. Since up to our knowledge, we are not aware of similar results for n greater or equal than 3. And the other problem is the order of the perturbation, meaning that I said in the beginning that we ask V to be bounded from HS to HS, because if we look at unbounded potential, the problem is much more difficult to study. So this is the reason why we look at our problem in dimension 2. Now, in order to state our theorem, I will now introduce the pseudodifferential setting and give the statement of the sufficient conditions that I was talking about before. So, first of all, let me define the class of operators we work with. Just quick notation, X and C are a pair of variables in R2, which is the notation for our variable in R4. And to define the class of operators, we need to start from this set, which is the set of symbols of order rho, which are functions smooth over the whole R4, and such that, looking at this condition with alpha and beta equal to 0, we ask for the function itself to be bounded by a polynomial in, homogeneous in X and C of degree 2 rho. And then we ask every time that we take a derivative both in X and in C to, at the right-hand side, obtain a bound with the degree decreased by 1/2 with our notation. So this is the definition, and it's just a requirement on smooth functions over R4, which have a nice kind of decay somehow. I don't want to focus on the abstract definition, but on the pair of examples that we will need. Unsurprisingly, the first one is the harmonic oscillator, which is, so I denote by little h0 the classical harmonic oscillator in R4, and with our definition, it is a symbol of order 1. Let me use this slide also to set the notation for the flow of H0, which I will denote by phi(H0), which is the classical flow. And then the other key example that we need is the set of homogeneous functions over R4. So we ask, so in this set we consider functions which are smooth over the whole R4, and such that we have homogeneity of order rho, so meaning that V evaluated in the point lambda x lambda c is equal to lambda to the rho V times V in X and C. Just to keep homogeneity, we added the last condition there, which asks for this condition outside of a radius of a ball of radius 1 centered in the origin. But it is just, if you want, technical to keep the homogeneity, the smoothness. Sorry. So this is the other example to have in mind. These homogeneous functions are symbols. It's not difficult at all to see, but I mean, it's just another example of symbols. And for simplicity, we will just now consider homogeneous symbols from now on, which is what we also do in our work up to smaller reminders, lower order reminders. So just for the sake of clarity, we will look at homogeneous symbols. And now we are finally able to define the class of operators that we use. So we consider a class of operators in which to each function in the set of symbols that I defined before, we are able to associate univocally an operator. I wrote the definition, which it's not important at all and maybe difficult to understand at a first sight. For this talk, it's not the point, but the strong point to have in mind is this univocal association of operators with smooth functions with this decay and vice versa. Again, the examples are the quantum harmonic oscillator, which of course has as associated symbol the classical harmonic oscillator. And let me now profit of this slide, if someone was wondering, to say that the classical harmonic oscillator is a symbol homogeneous of degree 2, and it belongs, it's a function homogeneous of degree 2, and it belongs to the set of symbols of order 1. This is just a matter of choices of the exponents, but I wanted to be precise because maybe from the last slide one could think that homogeneity was the same, but we just have with our notation this slight change. Homogeneous of degree 2 rho means a symbol of order rho. Okay, So, and finally, also, since we are looking at time-dependent potentials, let me also say that our potential is then a continuously dependent time-dependent operator valued in the set of symbols of order 0, just to give a meaning to the time variable. Okay, now let me state the sufficient conditions and the abstract result of Alberto that are a crucial point for our work. So, very quickly, given a time-dependent operator, we will need to work with its time average, which is defined there, since it is the average of the operator V along the flow of the operator H0. If V is time-dependent of order 0, this average is time-independent, of course, but it keeps the same order. So it's always a pseudo-differential operator of degree 0. Okay, this is the theorem that Alberto proves in 2022, and the requirements and the sufficient conditions for the potential to be a transporter are the following. He looks at the average of the operator and he asks, first of all, for this condition on the spectrum of the average, which is the existence of an interval such that the Lebesgue measure, which I denoted with these bars, of the spectrum intersected with such interval is positive. So, for example, this is what we will see. You are happy if you find an interval contained in the spectrum. And second, this inequality, which may seem a bit difficult to read, and is a kind of positive commutator estimate, which is a thing which is usually common to prove energy estimates like in our case. This estimate in the literature is known as Moore estimate, and the requirement is the following. So, forgetting about the technicalities, we have to look for an operator A such that the commutator of A with the resonant average with the average of V is strictly positive, theta is a positive value, up to a compact remainder, which is K, when localized in an appropriate region of the spectrum, which is given by the first condition. If these two conditions hold, V is a transporter. Maybe this, of course, this Moore estimate is not immediate at all, neither to understand nor to find a way to apply it. But as you can imagine, the main difficulty is to find the operator A. And now we move towards the statement of our result, because the reason why I introduced all this setup of pseudo-differential operators and symbols is that these two conditions that are given at the level of operators can now be translated at the level of symbols. So the strength is given by a set of results which are known under the name of symbolic calculus, or pseudo-differential calculus, and this kind of results, which allow to translate these conditions on requirement on the symbol. So hopefully on an easier setting. So in order to translate them, the first point is this. What we ask are requirements on the average of the operator V, which I just rewritten in the first line, and is what we defined before. What we look at is the symbol, the time-dependent symbol V, and we look at its classical average. So we compose it with the flow of the classical harmonic oscillator, and we average in time, obtaining this average of the symbol V. And the important fact is, which is known as Egorov theorem, is that I didn't write the precise statement, sorry, but the idea is that the operator given by the average of V has as associated symbol exactly the classical average of V. So the conditions that were given on the average of the operator can now be translated in conditions on this smooth function, which is given by the average of V. Okay, So the first condition was related to the spectrum of the average of V, and the nice result is the following. So we look at the symbol, given a symbol of order 0, which for us is the average of V, homogeneous of degree 0, then we can gain information which are very precise on the spectrum, looking just on the spectrum, sorry, of the operator, looking just at the symbol. So the spectrum of the operator associated with the average of V is equal to the range of V when restricted to S3. Maybe I said it very unclearly, but since the average of V is homogeneous of degree 0 outside S3, we can look at its restriction on S3, and thus the range of this average over S3 coincides with the range on the whole R4 minus the ball, which we are excluding for technical facts. And thus, the range of the average of V over S3 is, since the operator is, since the symbol is smooth, is an interval. And thus the requirement on the spectrum to have an interval such that the intersection is positive measure, etc., here is achieved just if the average of our symbol is non-constant. So we are pretty happy of this first translation. And then the second one is the crucial one, and is the translation of the Moore estimate at the level of symbols. So here I ask you to believe me a little bit, but the translation that one can do, thanks to some results of symbolic calculus, is the following. So if we find a symbol, so a smooth function, such that the Poisson brackets of the average of V against this function are positive in an interval contained in the image, so for some values in the range of the average of V, then quantizing the symbol, so looking at the associated operator, we obtain the operator that realizes the positive commutator estimates we were looking for. So it is not clear from this slide how one translates exactly the construction, and it was a bit technical, so for time reasons I didn't write it all, but it's not difficult, and the idea is that we are translating the operator estimate on a check on the Poisson brackets of functions over R4, which hopefully is an easier check to do. So now, given these two facts, we can finally state our result. So what we define is this set, calligraphic V, which is the sets of symbols just in a sentence which verify the conditions I gave before. So such that looking at the time average of the symbol, we find an interval in its image, so it's non-constant, and then we find another symbol which realizes positivity of the Poisson brackets. Then we have instability is what we were trying to say up to now. So every element in this set has associated operator, which is a transporter, which is given by Alberto's result. What we are very happy to say is that this set is again generic. So if we look at the set of time-dependent symbol homogeneous of order 0, this set is open and dense in this space, which is a Fréchet space. And again, I didn't want to spend too much time on the precise definition of the semi-norms, but it's a set in which it makes sense if you want to talk about open and density. And our set of symbols, it's generic. So again, instability is a very, very common fact and phenomenon for these equations, also in dimension 2. Okay, so this is our result, and I hope to have given an idea. Now let me say that the proof of the analogous result in dimension 1 was, it was possible to do it somehow directly, finding this symbol A, which is called the escape function, and I will now explain a bit, in a pretty much straightforward way, with some computations using action angle variables. So it was able really Alberto was really able to compute this function directly. And this is the reason why it is a problem to look at higher dimensional settings. Indeed, with our work, we started looking at a setup in which it was no more possible to compute directly the escape function and the symbol A, so we had to construct it somehow. So I hope, yes, to give an idea of the construction of the main elements in the construction we did. So now, from now on, the problem that we focus on is that of finding the symbol A, which realizes positivity of the Poisson brackets. Very, very informally, what is the strategy that we follow? So we look at the average of V, which is a smooth function over R4. We look at it as an Hamiltonian, so we study the classical Hamiltonian flow over R4 generated by the average of V. And thus, what we want to look for are conditions on these Hamiltonian dynamics, which are sufficient for the existence of an escape function, but at the same time generic, because what we want to prove is genericity of our set. And I think it is a good moment to say that the works that we started with our study were a first work by Colin de Verdier, Lors and Raymond in 2019, in which the authors construct an escape function with, I mean, we exploited their ideas, so in a way that it's similar to ours, but in a different topological settings. And then these ideas were then further developed by Colin de Verdier in a subsequent paper in 2020. So this was the starting point for our study. And let me very quickly motivate why we think it is important to look at the Hamiltonian dynamics in order to search for the escape function. Indeed, I just reported very quickly the notations for given any function H over R4, the Hamiltonian vector field associated with H, and the corresponding Hamiltonian flow. Because the requirement of positivity of the Poisson brackets means that if we look at this for a function A which has positive Poisson brackets with H, it means that if we consider A composed with the flow, Hamiltonian flow of H, and we consider this as a time-dependent function and we take the time derivative, what we find out is that this time derivative is exactly, of course, corresponds exactly with the Poisson brackets with H and A, and thus looking for an escape function means looking for a function which strictly increases but along the trajectories of the Hamiltonian flow. So this is the reason why it is important to look at the Hamiltonian dynamics in order to find conditions for the existence of A, if you want. Okay, so just to explain the conditions that we look for, let me just spend a second saying that these conditions, these Hamiltonians that we consider are now functions which are homogeneous of degree 0 over the whole R4. So forgetting for a second all the set of symbols, what we do now is finding an escape function for a smooth Hamiltonian homogeneous of degree 0 on the whole R4 minus the origin. So then it is just a technical fact to pass from symbols to this set, smoothing in the origin, if you want. So I will now denote with these brackets of V the homogenization. So I already have homogeneity outside the sphere S3, and I project thanks to homogeneity on the whole R4 minus the origin. Thus, what I define is given a value in the image of these brackets of V, of the homogenization of V, I define the energy shell, sigma omega 0, which now, thanks to homogeneity, is a cone, as a cone structure, and thus defining the intersection of this shell with S3, we are able to write it sigma topologically as R times Z omega 0, which is how we denoted the intersection of our energy shell with S3. And thus, with this definition, it is possible to also decompose the Hamiltonian vector field in a component which is radial, which is the first one, and the second one, which is a vector field that lives on the tangent space of the surface Z omega 0. So thanks to homogeneity, what I want to say in this slide is that thanks to homogeneity, we are able to decrease by 1 the dimension, if you want, of our problem. So our vector field XH is decomposed in this way, and we can now look at this tilde X, which is a vector field on the tangent of Z omega 0, which is thus a vector field on a surface, so on a dimension 2 manifold, which is smooth and is compact. So it is, if you want, an easier topological setup. Now, just hoping that with a wrong picture, the idea is clear. So, of course, we are working in dimension 4. So the picture is wrong since I plot everything in dimension 3. But the idea I was trying to convey is that we have a conic energy shell, and we consider its intersection with the sphere, obtaining the blue manifold, which is a dimension 2 smooth compact manifold, and we decompose accordingly the vector field. So what we will look at from now on is the red vector field, if you want, and we'll look for conditions on this vector field in order to find the escape function. So this definition is the definition of the sets of vector field we look for. So what we now ask is for our vector field X tilde to be a vector field of Morse-Mail type. The idea is the following. So let me start from the picture of Morse-Mail vector field, which is less aggressive. So the idea is the following. We have this smooth vector field over on a compact manifold in dimension 2. I plotted an example of a vector field which is of Morse-Mail type, meaning that we have a finite number of closed orbits and critical points. In this example, you see that we have just 2 closed orbits, which are the ones 1 and 2. This is the same plot with the flow lines, so maybe it is clear that this is a closed orbit, and this is another one. From periodicity, 0 and 2 pi are the same orbit, are identified. So we have a finite number of critical elements, if you want, which in this case are these 2 closed orbits. And then you see that all the trajectories, as time tends to minus infinity, tend to one of such critical elements. And as time tends to plus infinity, tend to another one, maybe the same, whatever they like, in this case to a different one. So these are the structural properties that we require. Maybe now, if we go back to the same definition, it is a bit less ugly. So there are finitely many singularities and closed orbits, all of which are non-degenerate. So all the orbits are either attractive or repulsive. Critical elements are either attractive or repulsive, if you want. And then alpha and omega limit set of each flow line is either a singular point or a closed orbit, which, if you want, is a bit more technical way to say that every orbit tends to a critical element either at time as time goes to minus infinity and as time goes to plus infinity. Why did I do this dynamical systems change? Because the important fact is the proposition that I stated. So the idea is that given an Hamiltonian homogeneous of degree 0 and the whole are 4 minus the origin, so in our setup, and looking at the vector field X tilde that I introduced before, the stronger fact is that if the vector field is Morse-Mail, then there exists an escape function. So we are able, and I will not talk about the construction, but we are able to use these dynamical properties in order to construct our escape function. So this is a nice news, but the nicer one, if you want, is that the reason why we choose this class of vector fields is that it is a famous result of 1962, that more small vector fields are generic in the set of vector fields in manifolds of dimension 2, which are closed and orientable. So let me stress now that this result holds just in dimension 2. So we are able to define more small systems in any dimension, but we have this genericity just in dimension 2. And this is the reason why in our work we are forced, if you want, to use dimension 2, because this is the construction that we do. So finally, informally, but this is the main proposition, if you want, needed to prove genericity. Indeed, what we are able to prove is that given a function h, which is again with the homogeneity properties that we require, we are always able to, and given any epsilon greater than 0, we are always able to find a function h epsilon, which is epsilon close to h, and such that the tilde vector field is more small. So for any Hamiltonian, we are able to move as small as little as you want, and find another one for which we have an escape function. So this is somehow the main idea of how we prove genericity in our case. So clearly, the facts that still needs to be understood are related to, first of all, the same kind of construction, but in different topological settings. So if we can look for other Hamiltonian dynamics, which reduce to the study of dimension 2 vector field for which we have the construction. And then clearly higher dimension, and as I said, more small systems are no longer generic. So we need other dynamical requirements. And finally, unbounded potentials, which are much more difficult to tackle. But again, the idea that one can have in mind is always to use this translation of the problem to a problem of Hamiltonian dynamics. So this is the strength that we hope to use, but this has still to be done. So thank you very much. And here's a little bibliography of the stuff that I talked about.
Teresa,
thank you.
Are there questions from the audience?
I hope I can also look if. Okay.
I saw that in dimension larger than 2, I think the vector field satisfying the small
more small condition, yes.
Condition are not more generic.
Yes.
Can you, is it possible to characterize the family of vector fields in which they are generic? The closure of the.
So the vector fields are no longer generic in dimension greater than equal, dimension strictly greater than 2. I'm not sure we are able to characterize the closure of more small sets. There are some results. So more small sets, as you can imagine from the picture, at least, and the definition, are stable under perturbation and form an open set. So I'm not sure we can characterize the closure. I have no idea, of course, but I don't have in mind a direct way. But they are a nice set also in higher dimension. Yeah, the problem is, of course, that in dimension 2, the dynamics is not chaotic, if you want, so it's pretty much straightforward to see that these trajectories are, if you want, the only one which are generically possible, whilst in already in dimension 3, all the attractors that one can think of are much more chaotic. So I think that really this kind of sets is not the right one to look at in higher dimension. in the works by Colin de Verdiel or Raymond, and this is also what we did, but for the sake of simplicity, I just talked of more small sets. In our works, we look at a wider class of sets which contains more small ones, which is a class of sets in which you ask for the existence of a global attractor and a global repeller. So you no longer ask for all of these conditions, but you ask that all trajectories tend, as time goes to minus infinity, to a certain set that you kind of don't worry about as long as it is an attractor. And the same happens as time goes to minus infinity. And this class of sets is clearly larger and seems to be much more promising in higher dimension. So this is the idea, to forget about more small vector fields and use the structure in a more abstract way if you want. But yes, thank you.
I had another question. You computed the average of the Piombino.
Yes.
And you can do this, I think, because your Hamiltonian is a harmonic oscillator, so the orbits are closed. If you don't have periodic orbits of the unperturbed Hamiltonian, you can do something.
So, I mean, the idea, you mean
for other Hamiltonians. You
Okay.
can do something for other Hamiltonians in which the...
Okay, so you mean we have H0 that we know is the harmonic oscillator, and we are happy about periodicity of the orbits. So we look at a potential that allows us to compute the resonant average. So the idea, this is the particular construction we did, yes. The idea is that in general, you can look at other equations, but from which you are able to extract a higher order operator, which usually is a resonant operator. Let me try to say in an understandable way, which is time independent and on which you can thus carry on this construction. So since we were working with this kind of Schrödinger equation with the harmonic oscillator operator, we did the resonant average with respect to the flow. But for example, now we are looking at a transport problem in which we are, in our case, in dimension 1, but this is not the point. You have, oops, here it is, okay. So you have time derivative equal to the mass term plus this is a reminder that we don't care about, but the higher order operator is this one. So in this problem, we consider a periodic setup, of course, because I mean you must have some time, somehow periodicity to compute your average, because otherwise you don't know even that it is computable. But if you translate the problem in periodic setting, but no more periodic orbits on the principal operator, you are able to extract the resonant part of this operator, which is time independent, and so you can carry on the analogous construction. So if you have another Hamiltonian in which you have a periodic, for which the solutions are periodic, you can do what we did in our work. Otherwise, you must be able to reconstruct somehow a setting from which you gain periodicity and you extract the resonant part. I hope this is the answer somehow.
More curiosity than a question. The notation on the pseudodifferential operator, which is OP and W.
C. Yes.
Is W.
This is,
Would
sorry.
Wigner-
The W is Weil, it's not Wigner, I'm sorry.
Is it sorry?
Weil.
Okay, what are they?
So the idea is that in this definition, here you see that we have, just sorry for the real definition, then I give the motivation. Here you have 1 half x plus 1 half y. If you want, you can use tx plus 1 minus ty for any t, and obtain all a set of quantizations, of definitions, of classes of operator, which are indexed by the index t. So W corresponds to the index 1 half 1 half. Then there is the standard one, which is when t is equal to 0, 1 with what I said, but in the extremal, which are also widely studied. This is convenient for us because Weil's quantization has very, very nice properties. One for all is that real functions, real symbols correspond to self-adjoint operators, which is what we want, self-adjoint of our potential, and we automatically have it here. But we are not cheating on the other end because all quantizations define the same class of operators at the highest order. So if you have an operators in the Weil quantization, then for any other quantization, you have the same operators up to lower order reminders. So it is not the only choice for which everything is nice.
Okay, if there are no more questions, let's thank again.
Thank you very much, and thank you also for everybody. Thank you very much also online for joining. Incredibile.